Today, we're going to tackle something that's, well, pretty literally cool. Magnetic refrigeration.
Definitely cool. And we know you're looking for substance without getting bogged down in technicalities, and that's exactly what we aim for in these deep dives. So we're going to be exploring magnetic refrigeration, a technology based on something called the magnetocaloric effect, looking
Yeah.
at its history, the science behind it, and how it might revolutionize cooling technology across the board, from like niche scientific equipment to something as common as the fridge in your kitchen. We've dug into a ton of sources to bring you the full picture, from the basics to the latest developments.
Okay, so let's get right into it. What exactly is this magnetocaloric effect? What are we even talking about here?
It all boils down to this. Certain materials actually change their temperature when they're exposed to a changing magnetic field. So imagine you have a suitable material and you apply a magnetic field to it. What happens is the material will actually heat up. It releases heat into its surroundings.
So magnetism makes it hotter. That sounds kind of counterintuitive if we're aiming for refrigeration.
Yeah, you'd think so, right? But here's the key. When you remove the magnetic field, the material goes back to its original state. And as it does that, it reabsorbs heat, which makes it cool down.
Okay.
The trick to turning this into a refrigeration system is to create a cycle of this effect. So first, you let the material heat up under a magnetic field. And while it's hot, you have to get rid of that extra heat. And then when you remove the magnetic field, boom, it's ready to absorb heat from its surroundings and get colder than it was initially.
So it's a two-step process. You expel heat through magnetization, and then you cool down through demagnetization. Now, I came across this term, adiabatic demagnetization, in the research. Is that just a fancy way of describing that cooling step?
That's exactly what it is. It's the term that physicists, especially those working with really low temperatures, use to describe that cooling part. And adiabatic just means that ideally, the whole process happens without any exchange of heat with the surrounding environment. It's like a perfectly insulated system.
Adiabatic demagnetization. Got it. But let's get a little more specific. How does this whole magnetic field and material interaction actually work at a microscopic level?
Yeah.
How does it lead to this heating and cooling?
Well, you got to look at the magnetic properties of the material itself. You can picture it as having these tiny little magnets inside called magnetic domains. When you apply a magnetic field, these domains tend to line up in the direction of the field. It's like they want to get organized.
So the field creates order.
Exactly. And this ordering actually decreases the material's magnetic entropy. It becomes more organized, less random. Now, when you lower the magnetic field, especially if this happens in a perfectly insulated system, the material wants to go back to its more random state. And this is where things get interesting. The material's own internal thermal energy, the vibrations of its atoms, that's what drives this disordering process. And to become more disordered, those magnetic domains need to absorb some of that energy from the material's internal vibrations. So as they absorb this energy, the atoms slow down a little bit, and guess what? That means the overall temperature of the material drops.
It's kind of like the reverse of how heating something up can destroy its magnetic order. Like what happens when you go above a material's Curie temperature, right?
You got it. At the Curie temperature, the heat energy messes up the aligned domains. But here, the total energy in our isolated system basically stays the same. It's just that the magnetic field, which was forcing the domains to be ordered, is gone, so now the existing thermal energy can create more disorder. That's how that energy redistribution happens, leading to a drop in temperature.
So we're essentially tricking the material into using its own heat to mess up its magnetic order, which results in it getting colder. Now, are all materials equally good at this? I know gadolinium gets mentioned a lot in this context.
Yeah, gadolinium is sort of the classic example. It shows this temperature change pretty clearly. It heats up when you apply a magnetic field and cools down when you take it away.
Makes sense.
But the really exciting part is that certain alloys, they show a much, much stronger effect. Like there's this one called GD5, Sci2D2, which is a bit of a mouthful, I know.
Just GD5 side, GD2, yeah. Not the catchiest name.
Haha, no, not really. But it's remarkable because it shows something called a giant magnetocaloric effect. It's way stronger than plain old gadolinium, so you get a much bigger temperature change for the same magnetic field strength. And on the flip side, if we go to the extreme low temperature end of things, an alloy of praseodymium and nickel, PrNi5, is pretty mind-blowing. They've actually used it to get within just 1 millikelvin of absolute zero.
Wow, that's like almost as cold as it gets. Now, is there a way to quantify this magnetocaloric effect? Can you predict how well a material will perform? I think I saw an equation
Oh, there
somewhere.
definitely is. The change in temperature, what we call ATAD, it can actually be described by an equation that takes into account a bunch of the material's properties. Like there's the initial temperature, T, how much the magnetic field changes, H, the heat capacity, C, and the magnetization, M.
Right.
It's a pretty detailed equation, but basically what it tells you is that you get a bigger magnetocaloric effect if you have a big change in the magnetic field, a material that doesn't need much heat to change its temperature, and a material whose magnetic properties are very sensitive to temperature changes.
So you're saying we want a big magnetic swing, a material that's easily swayed by temperature, and one that doesn't hog all the heat for itself?
Yeah, exactly. And importantly, this temperature change, Ted, is directly related to the change in the material's magnetic entropy, which is AS. The bigger the change in magnetic entropy you get when you change the magnetic field, the bigger the potential temperature difference you can achieve for refrigeration.
Entropy, that's basically a measure of disorder, right?
Yeah, exactly. It's about how random things are. And a magnetic field, when applied, forces some order upon those magnetic domains, so it reduces the entropy.
Okay, so less randomness, more cooling potential. Now, how do we actually go from this effect, the heating and cooling, to a working refrigerator? I mean, it's a cool trick, but how do you make it a continuous cycle that can actually extract heat from something? The sources mention some parallels to other cooling systems.
You're right. There are some similarities to the Carnot cycle and the vapor compression cycle, which is what most fridges use these days. The difference is, instead of changing the pressure like in those systems, here we're playing with the magnetic field. There are four main steps to this process.
Okay, let's hear them.
So step one is what's called adiabatic magnetization. We take our magnetocaloric material, which is our refrigerant, and we put it in a perfectly insulated environment. Then we crank up the magnetic field.
Okay.
As we increase the field strength, those magnetic dipoles in the material line up. This reduces the material's entropy and its ability to hold heat. But the total entropy has got to go somewhere, so the material itself heats up, reaching a temperature of T plus dad.
So we're making it hotter by magnetizing it in an insulated space. What's next?
Right. Now comes the second step, which is called isomagnetic enthalpic transfer. We keep the magnetic field strength constant, but we bring in some kind of coolant, maybe helium gas or liquid, and let it come in contact with the material. This coolant takes away that extra heat that we generated in step one. It's a heat sink. Once our material has cooled down to a temperature close to that of the coolant, while still under the magnetic field, we isolate it from the coolant.
Okay, so we've heated it up, we've removed that excess heat, all while it's still magnetized, and now we're ready for the cooling part.
You got it. Step three is where the real cooling magic happens. This is adiabatic demagnetization. We make sure our material is back in its insulated state so no heat can leak in or out, and then we lower the magnetic field. As the field weakens, those magnetic moments in the material can finally start to become more disordered. To do that, they absorb energy, and this energy comes from the material's own internal vibrations, causing its temperature to drop.
It's kind of like the reverse of what happened when we magnetized it, right?
Exactly. We're shifting energy from thermal entropy to magnetic entropy, and that's where the cooling comes from.
So now we have a material that's colder than it was at the start of the cycle. What's the last step to make it a true refrigerator?
The last step is isomagnetic entropic transfer. We keep the magnetic field at its lower level and bring our cold material into contact with whatever we want to cool. Because our material is colder, heat naturally flows from the warmer environment into the colder material. This cools down the environment, and once it's reached equilibrium, the cycle starts all over again.
Beautiful. So we use a magnetic field to force the material to release heat, and then we remove the field to make it absorb heat. It's a really clever way to do cooling. The sources also mention this specific application called the adiabatic demagnetization refrigerator, or ADR. How does that fit into the bigger picture?
The ADR is basically a way to put this cycle into practice, especially if you're trying to reach super low temperatures. And the trick here is to use a really strong magnetic field to control the entropy of the refrigerant material.
So you're saying a strong magnet is key for this specific technique?
Absolutely. In a typical ADR setup, you start by applying a strong magnetic field to the refrigerant while it's in contact with a heat sink, something like liquid helium, which is already really, really cold. The refrigerant, wanting to reach equilibrium, releases energy to this heat sink because the strong magnetic field is forcing it to be more ordered, which lowers its entropy. And then you break the contact with the heat sink and switch off the magnetic field. Now, as the field decreases, the refrigerant wants to become more disordered. And to do that, it needs energy, which it draws from its own internal vibrations, making it even colder than the liquid helium it started with.
So you're saying the liquid helium gets it cold, and then the magnet trickery takes it even colder.
Exactly. Now, in real ADRs, instead of just flicking the magnet off, they usually decrease the field strength gradually.
Okay.
This allows for a more continuous cooling, which is more practical. But there's a limit, of course. As the magnetic field gets weaker and weaker, the cooling power also goes down, and any stray heat leaking in from the surroundings starts to warm the refrigerant back up.
Makes sense.
Eh.
So it sounds like choosing the right material is crucial for all of this to work. What kind of materials are actually good candidates for this magnetic refrigeration thing, especially if we're talking about everyday things like refrigerators?
You've hit on a very important point. So this magnetocaloric effect, it's something that all magnetic solids have. But the effect is strongest near the material's magnetic ordering temperature. This is the temperature where the material switches between different magnetic phases. Now, for something like a fridge, you'd ideally want this temperature to be near room temperature, right?
That makes sense.
Another key factor is how much the magnetic order in the material changes during this transition. A big change means a bigger temperature difference, which is what we want.
Okay. Now, I remember the sources mentioning something about first order and second order phase transitions.
Yeah.
Is there a practical difference between those for magnetic refrigeration?
There is. A first-order transition, it happens abruptly. The magnetization of the material changes suddenly when you reach that temperature, and it usually involves what we call latent heat, kind of like the energy needed to melt ice. A second-order transition is more gradual, and there's no latent heat involved. So gadolinium, for example, has a second-order transition, which means it behaves pretty predictably and doesn't have much hysteresis. That means it responds smoothly to changes in the magnetic field.
So predictable and well-behaved is a good thing. But didn't you say the GD5, Sci2G2, with its giant magnetocaloric effect, happened below room temperature? Does that mean that maybe these first-order transitions are better in terms of how strong the effect is?
That's a great observation. You're absolutely right.
Right.
While gadolinium is reliable, the materials with this giant magnetocaloric effect, often tied to first-order transitions, they can really pack a punch. They give you much larger temperature changes for the same magnetic field change. GD5 Sci-G2 is a huge discovery, but the problem was that its transition temperature was about 270 Kelvin, which is too cold for a typical fridge. Now, since then, we found other alloys that show this giant magnetocaloric effect. There are variations of the gadolinium silicon-germanium mix, some lanthanum iron silicon hydrogen compounds, and also manganese iron phosphorus arsenic compounds. The problem is that many of these rely on rare earth elements like gadolinium, which are expensive, making them less appealing for widespread use.
So cost is a factor here. Are there any other options that might be more affordable? I saw something about nickel manganese X alloys, also called Heisler alloys.
Heisler alloys are definitely promising. Some of them have Curie temperatures that are right around room temperature, and they can also undergo these martensitic transformations, which basically means their crystal structure changes, and that can boost the magnetocaloric effect. And fun fact, they also show this thing called the magnetic shape memory effect. You can actually change their shape with a magnetic field.
Wow.
Back in 2014, GE announced they had a working prototype magnetic fridge using a nickel manganese alloy, so things are definitely moving in the right direction.
That sounds exciting. But even so, it seems like we're still a long way from ditching our regular fridges. The forces mentioned that to replace the current vapor compression tech, we need much better, cheaper, and more abundant materials, and ideally something that works with weaker magnetic fields, maybe even just permanent magnets. We don't want to have to install a giant superconducting magnet just to keep our milk cold, right?
Exactly. The Holy Grail is a material with a strong magnetocaloric effect over a wide range of temperatures. And that works with magnetic fields of 2 Tesla or less, something you can get with a good permanent magnet. That's where a lot of the research is focused right now.
Now, taking a slight detour here, the sources also talk about these special materials for reaching extremely low temperatures, things like paramagnetic salts and nuclear demagnetization. Those sound pretty specific, like something you'd only need for specialized scientific research.
You're right, they're pretty niche, but super important for certain fields. Paramagnetic salts, things like cerium magnesium nitrate, they were actually the first materials people thought about for magnetic refrigeration. The interesting thing about them is that their magnetic properties come from the electron shells of the atoms. ADRs using these salts, they usually work with liquid helium cryostats as the initial cooling stage and can get down to temperatures between 1 and 100 millikelvin with relatively modest magnetic fields, like around 1 Tesla.
Right.
These systems are still interesting today for use in space and in labs where you don't want to deal with the complexities of dilution refrigerators, which is the other main way to reach these ultra-low temperatures.
So there are benefits, even though it's a much older technology. But I guess there's a limit to how cold you can get with these paramagnetic salts.
Yes, there is. When you get down to really low temperatures, they tend to become diamagnetic or ferromagnetic, and that messes up the paramagnetic properties you need for the cooling to work. To go even colder, you need something called nuclear demagnetization refrigeration, or NDR. This one uses the magnetic dipoles of the nuclei of atoms, which are much weaker than the ones from electrons.
So we're using the magnetism of the atom's nucleus to get even colder? That's wild.
It is, and this lets NDR get to crazy low temperatures, like below 1 microkelvin. But because the nuclear magnetic moments are so weak, you need extremely strong starting magnetic fields, usually 3 Tesla or more, and you need to pre-cool the material using either a dilution refrigerator or those paramagnetic salts we talked about. It's a multi-step process to reach the absolute coldest temperatures.
That's pretty credible. Now, coming back to the practical side of things, what's the story on the commercial development of magnetic refrigeration? It seems like this technology has been in the works for a while.
Oh yeah, it definitely has a long history. A big milestone was in 2001 when they did a proof of concept using off-the-shelf materials and permanent magnets, and it worked at room temperature. Then in 2007, a group at Riese National Laboratory in Denmark reported achieving a temperature span of almost 9 Kelvin. They were really optimistic about seeing commercial applications by 2010.
So there was a lot of excitement early on, but it seems like those initial hopes didn't quite pan out. The sources suggest that by 2013, it was still mainly useful for those ultra-low temperature applications. What were the roadblocks for making it work at room temperature?
It turned out that scaling up the technology and making it affordable was trickier than they initially thought. Building reliable systems with efficient heat transfer and magnetic materials that could withstand repeated magnetization and demagnetization cycles, it was more challenging than expected. But things started to change around 2014. That's when Cooltech Applications, a company that was really pushing this tech forward, announced their first commercial magnetic refrigeration equipment. And a couple years later, in 2016, they launched their first fully commercial system.
It sounds like Cooltech was a major player in making this happen. I read that they even presented at the 2015 Consumer Electronics Show with Haier and BASF claimed that it was way more energy efficient than traditional compressor-based systems.
Yeah, that was a pretty big deal. It showed the potential for magnetic refrigeration in consumer products. Cooltech also teamed up with a medical company to develop a magnetic medical cabinet, and they also came out with a frozen heat exchanger based on this tech. By 2017, they had even built a working 500-liter fridge, showing that things were getting serious. And then in 2018, they unveiled a 15-kilowatt prototype, which was the biggest one anyone had built at that point.
That's a pretty impressive track record. But then the sources mentioned that Cooltech went bankrupt. What happened there?
Yeah, that was a real shame. Despite all the technological progress they made, they ran into financial problems and had to file for bankruptcy in 2018. But the story doesn't end there. Some of the key people from Cooltech, they founded a new company called Magnoric in 2019, and they bought up all of Cooltech's patents. They've continued the work, and everyone agrees that Cooltech's prototypes were some of the most advanced out there.
So it wasn't a complete dead end. The technology survived. What are the main challenges that are still holding back magnetic refrigeration from becoming more widely used?
One of the big ones is hysteresis, specifically the thermal and magnetic kind, which is especially a problem in those materials with the giant magnetocaloric effect, the ones with the first-order transitions. Hysteresis basically means that the material doesn't respond perfectly to changes in the magnetic field. It wastes energy, which hurts efficiency. Another focus is finding materials that work really well for specific applications, like in spacecraft, where you need something super reliable and efficient, even in extreme conditions. And when you compare magnetic refrigeration to the vapor compression systems that we use today, the magnetic ones still have a lower coefficient of performance, which is a measure of efficiency. But to be fair, our regular fridges aren't as efficient as they theoretically could be either.
So there's still room for improvement on both sides. The sources also briefly touch on some newer developments, like something called anisotropic effects, and also combining magnetic refrigeration with geothermal energy. Those sound like pretty interesting directions to explore.
They're definitely exciting avenues. In 2014, researchers found a giant anisotropic magnetocaloric effect in a material called Holman 205. It's pretty cool because it works at very low temperatures, around 10 Kelvin, and the change in magnetic entropy depends on which direction you apply the magnetic field.
Hmm.
This could lead to simpler cooling systems that just rotate the material within a constant magnetic field, so you wouldn't need to switch the field on and off.
That sounds pretty clever. And what about the geothermal link? How does that work?
That's the geothermic concept, which came out in 2015. The idea is to use low-temperature geothermal energy to power a magnetic refrigeration system. They actually built a test system using gadolinium as the refrigerant and geothermal water as the heat source. And it worked. They were able to produce cold water with it even under a load. So that opens up some possibilities for things like cooling systems for buildings.
So it's like combining two potentially more sustainable technologies into one. Now, as we wrap up this deep dive, let's step back a bit and look at the history of this whole magnetic refrigeration thing. It's clearly not a new idea.
Oh, definitely not. The magnetocaloric effect was actually first observed way back in 1881 by a German physicist named Emil Warburg. Then in 1917, two other physicists, Pierre Weiss and Auguste Piccard, they did some work that helped us understand it better, but the real breakthrough came in the late 1920s. That's when Peter Debye and William Jack, working independently, came up with the idea of using adiabatic demagnetization for cooling. Both of them ended up winning Nobel Prizes for their work on low-temperature physics.
So the basic science has been around for almost 100 years.
Yeah. And the first time anyone actually demonstrated this cooling method was in 1933, when Jack and his colleague D.P. McDougall used it to reach 0.25 Kelvin, which is crazy cold. There were some more developments between then and the late 90s, but a big jump happened in 1997.
What happened then?
A guy named Carl Geithner at Ames Laboratory, he built the first magnetic refrigerator that worked near room temperature. That really got a lot of people interested and picked off a ton of research into finding better materials and designs.
Makes sense. And then there was the discovery of the giant magnetocaloric effect in 2002, right? And it happened in materials that were more common and cheaper, like those manganese, iron, phosphorus, arsenic alloys.
Exactly. That was a game changer. Since then, there's been a ton of research and development with people trying out different magnetic fields, from weak permanent magnets to super strong superconducting magnets.
The sources also include a table listing a whole bunch of different room temperature magnetic refrigerators that have been developed over the years. It's pretty amazing to see the variety of approaches people have taken.
Oh, yeah. It really shows you how much creativity and innovation there is in this field. The table lists all sorts of different designs, like reciprocating and rotary systems, different types of magnets, and a whole range of materials they've tried, from simple gadolinium spheres to thin films and layered beds to those fancy new alloys.
Right.
It also gives you an idea of how much cooling power they were able to achieve, the maximum temperature difference, and their efficiency.
Well, this has been a truly fascinating deep dive into the world of magnetic refrigeration. It's clear that this technology, even though it's still under development, has the potential to be a much more environmentally friendly way to cool things. We've seen it work at super low temperatures and at temperatures we need for everyday life.
I totally agree. And what makes it even more exciting is that the progress in material science is what's driving this field forward. The search for that perfect material, one that's cheap, efficient, and works with normal magnets, that's the key to unlocking the full potential of magnetic refrigeration.
So here's something to think about. Imagine if we did find that perfect material. What would it mean to have efficient and sustainable magnetic refrigeration in our homes, businesses, and industries? How would it change the way we use energy and impact the environment? And what completely new applications might emerge from this technology? It's a really exciting area to keep an eye on. Thanks for joining us on this deep dive.